Just sort of review one. So, as I think I said this morning, let me turn the light. So X is a projective variety over a field K, and little k inside K is a subfield. You say that X is defined over little k if there exists Y projective over little k such that X equals, well, I write Y tensor over little k with big K, or in other words, Y equals, X equals Y, the Plática product, over a spec of little k, spec of big K. So, I mean, if another way of saying this is that if X, since X is projective, it's sitting inside the projective space is defined by some homogeneous polynomial equations, and this is saying there's a isomorphism of projective varieties, and this is some other variety, where in fact those polynomial equations for the second variety actually have coefficients in little k. So there's some obvious questions. Number one, does X have a minimal field of definition? Number two, if it does, is this field unique? And number three, so even if 1 and 2 are true, how do you find such a field? I mean, just to emphasize why, I mean, let's say take question 1. So I'm not actually going to give examples here, because in some sense, what's the right way to say this? I mean, in a certain sense, I can't give an example for why number 1 isn't true. In a certain sense, number 1 is true. But I mean, so let me give an example. Suppose little k equals, let's take f q bar, f p bar, so p is prime greater than 0, and suppose k is little k join t. And now suppose, by the way, so a piece of terminology I should have said here. Let's see, where should I put this? So I'll just write this over here. I'll also say that X descends to K it's defined over K. Okay, so suppose, so we have X over K, project a variety. And now you could ask, you can say, well, let's suppose that K descends X, yeah, thanks. Descends the field generated by t to the p to the n for every n. Oh. Well, yeah. Does it descend to the intersection okay? And it's not at all obvious that this should be true. Or maybe I should say it was not obvious to various people. This should be true. You could also imagine a situation that you would have K, little k, and little k primed, where X you could have a situation potentially where K and K primed are minimal. In other words, there's no subfield of K or K primed over which X is defined, but yet, K is not equal to K prime. And then, 3 speaks for itself. I mean, even if you do know that a minimal field exists, and if it exists, that it's unique, how do you actually find it? And now, one thing I should say is, in some sense, so this example is perhaps might be a little bit misleading. So here's a remark, which is that if sigma, if X is defined over little k, so X is isomorphic to y times spec k over little k, and let's suppose sigma from k to k is an automorphism of big K fixing little k, well then clearly if we let sigma act on this product by the second factor, sigma lifts to X. So this leads to what was classically called this definition. Unfortunately, I don't. I guess I never checked if I could have who originally came up with this. This is a classical definition, which is the field of moduli. I'm pretty sure this terminology goes back. I want to say it goes back to the 1950s, but I don't swear to this. So it's K, let's see, what do I want to say here? So it's the fixed field of K under the group where G inside the automorphisms of K is the group set of all of sigma the set of automorphisms of K which lift to automorphisms X. So this is clearly a group. So you have this group of automorphisms, and now you can just say, okay, let's look at the fixed field. And so sort of there's a natural question, which is, is X defined over its field of moduli? And this sort of, there are various situations in which this is actually, not just an abstract question, it's a question of importance. When you look at, let's say, an abelian variety, you might want to know is it defined over its field of moduli? You construct, there are connections to this field of moduli. You can sort of construct the field of moduli, using automorphic forms or whatever. There's sort of very concrete questions people like Shimura would ask about this. And it was known that the answer is no. Now, I have to apologize. I should have. One of the things that maybe we hadn't had such a good lunch, I would have checked before this talk, is there's an online book, there's a book of collars, which is either available online or which I have sitting on my laptop, where there's some very simple examples. But the examples involve, let's say, sort of classical Galois extensions. In other words, you can find some field in which there's some you can descend to various subfields of which the big field is a Galois extension, but you can't descend to the intersection of the fields. Okay, well, so this sort of notion of the field of moduli, therefore, maybe isn't quite the right notion. So what can you say? Well, let's go back. So what's the connection? With the Kodaira-Spencer limits. Well, remember that if I have a smooth projective variety of X, and the smooth projective variety, maybe at this point, now I want to assume X is smooth and projective at the moment. And K is a characteristic 0. And I want to assume that, let's say for simplicity, but the example I talked about this morning is when K is the function field of a curve. So we could have had K sort of is some finite extension of the rational functions over some little k. So that's not going to be really so terribly important in a moment. But what's in this situation, so here we have So what's always true in these situations, here this is a curve over little k, is if you look at the equations for x, so these are polynomial equations with coefficients in capital K. Now, if I take some affine curve whose function field is k, so this is some, so its coordinate ring will be some extension, so the coordinate ring of C will contain kt. A ring like this basically consists of the subring of elements of K whose denominators lie in some fixed multiplicative set, or sort of that you get by just inverting some finite number of primes. And on the other hand, if I look at this x, its equations have finitely many coefficients and involve finitely many denominators, and so such a variety always actually comes from something which is which is really given by a family of varieties over a curve. I just look here at the equations and really just think of the equations as having coefficients in a ring like this. And so I can always, by maybe localizing a little bit more, assume that this extension is étal, in which case if I look at delta equals d by dt, so this is étal, then d by dt extends to a derivation. So delta sort of extends uniquely to the coordinate ring of this curve, and it's a non-vanishing vector field on C. And as such, now the Kadara-Spencer class, you can think of it in one of two ways. We can look at the tangent bundle of x to, I can give this a name, let's call this pi up a star of the tangent bundle C. But this is just trivial. This is basically just the trivial bundle spanned by delta. And then here we have the relative tangent bundle. Now, if I want to think of these in terms of sheaves, I can dualize, and I can look at omega 1, pi up star omega 1 c, the sheaf of derivations, omega 1 x over k to omega 1 x over c. And so here we have, this is generated. So this is a trivial, this is isomorphic to, sorry, like this, isomorphic to OC times dt. And so the Kadara-Spencer class is the class in H1 of x with coefficients, I trivialize this, of the tangent bundle, and actually I'd write theta x over c. So this is the sheaf of sections of the tangent bundle, which is the obstruction to the vanishing, the obstruction, sorry, I should say, the splitting of the sequence. So this is the obstruction to lifting delta x. Now, as I mentioned this morning, it's a well-known fact that if the Kadara-Spencer class is trivial, then the family is isotrivial. And I want to give I can, a very quick sketch of the proof of this. It's sort of odd. I mean, I'm not sure where this is really explicitly written down. As a result, you sometimes see some odd statements, some odd, sort of unnecessary hypotheses added.
I have a feeling you can take it out of some references theory of watch.
Well, I think the answer is exactly no, because that's analytic in some sense. I mean, in other words, this is really a statement which is not about the complex numbers. It's really about, so it really has to do with versal deformation theory.
Yeah, no. If your characteristic 0.
Yeah, we don't want to use Hodge theory. Absolutely, categorically don't want to use Hodge theory, because at the end of the day, we want to be able to do something in characteristic P. Okay. And I mean, so what is the proof? And this really, as I said, goes back to the whole sort of Grodnik school of deformation theory. Okay, so the key point. So let's draw a picture. So here you have C. Here you have this family. You have a point I'll call P. You have this vector field here, delta. And here's X. And let's call, I'm going to write Roman XP is pi inverse of P. So I want to emphasize this is different from any kind of localization. This is the closed fiber. Okay, so, and now we're going to assume that delta lifts. So proof. So suppose delta tilde, the lift. All right, so in other words, that's given by, so you have a section delta of this guy, and it lifts back to a section of this guy. Okay, well, as I said this morning, the way you would do this complex analytically, this gives you an ordinary differential equation. You simply solve the ordinary differential equation. Now to break geometry, how do you solve an ordinary differential equation? Well, actually, it's way, way easier than it is in the immediate post-calculus class. And here's, I want to say if we were crazy enough, how we'd explain it to our students. Well, you have delta, you have this derivation. So let's consider the exponential. So maybe I should just say, before I do that, so delta goes from OC to OC, and delta tilde goes from OX to OX. So these are so little k linear sheaf homomorphisms. Okay, so let's look at the exponential of delta. Well, what is the exponential of delta? That's a map from OC. And now I want us to be a little bit careful about what I mean by power series. So I'm going to say this. I don't really mean the sheaf. How shall I put this? I guess I want to be careful. I really mean the pro system consisting of OC. What I really mean is this. In any case, or I guess you could look at the pre-sheet, the power series pre-sheet.
Inverse thing?
No. I mean, no, the point is precisely that you don't want to try and make inverse and direct limits commute, because that's generally a bad idea. Okay, so what is the exponential? It stands an element r, the sum delta I to the r, t to the I over I factorial. Okay? So r here, if you like, is an ox of u for some open oc of u, I should say, for some open in C. Okay? Now, the thing is that if I look so at P, this induces a ring homomorphism from OCP to OCP which if I then reduce so let's see, somewhere here I should have said this. I now want to assume that K is algebraically closed. So this gives you a homomorphism. Just reduce mod, so this is just reduce mod the maximal ideal. And now the thing is, this induces an isomorphism on the completion of this local ring to the formal power series, or if you like, a compatible system of.
Right, this capital K or little k? When you say I assume k equals k bar.
Little k, thanks.
Right. Makes sense.
Okay.
Things in characteristic 0?
Things are absolutely in characteristic 0.
Okay.
Yeah. Somewhere back here.
Exponential half.
Oh, I missed that.
Yeah. Okay. Now, I mean, if you think of delta as giving you a differential equation, this is the formal solution of the differential equation. So this map, if I think of this as a map of schemes, this actually gives me a map from sort of the line into the curve, and this actually has this sort of the usual property that you expect for a flow. Actually, here there's nothing. Maybe I'll skip over this, what I was about to say for 1 second. It's not immediately relevant. Okay, so now go back to the family. Where's the picture over here? I guess, yeah, no, I erased it. I really want now this picture. So here's P, and now we've got delta tilde. And delta tilde, I can look at the exponential of delta tilde. That gives me a map from OX to OX, which I can then compose. I can reduce modulo maximal ideal. And what this actually gives us, this induces isomorphisms from OX mod MP to the n to OXP of T mod T to the n. By exactly the same logic as in the curve case. So in other words, you can think of this as the flow gives you a local trivialization of the family in an infinitesimal neighborhood of the fiber. Okay, so we're almost done. So this really constitutes, this is actually what's called an isomorphism of formal schemes. So this is the completion of X along XP to XP, sort of tensor with what's called a formal spectrum of the power series ring. But this is actually simply a very fancy way. I mean, notice for each n, this is an iso of sheaves supported, well, actually really sheaves on the topological space XP. And so what an isomorphism of formal schemes means is it's really just a compatible system of such isomorphisms of sheaves on XP. Okay, so somehow you've now collapsed everything exactly onto this closed fiber. Now I said earlier on, it's always, generally speaking, a very bad idea to try and commute inverse and direct limits. But there's a certain sense in which, so for example, if you have a module over a polynomial ring, you can either complete the module with respect to powers of t, or you can take the tensor product of the module with the power series ring. And these two things are different unless the module is finitely generated. Well, the corresponding statement here is Rodendiek's formal gaga, which says that if X is projective over, well, really over C, then, or really, I really just need to know over maybe just over this local ring, then this formal isomorphism comes from an isomorphism of well, really, I'd sort of say sort of tensor over well, I should let me write this way. So if you have an isomorphism between this ring and this ring, so, and by this isomorphism, you can think of this and this as projective varieties over this ring. And Rodendiek's formal gaga says you have this formal isomorphism between these two projective varieties. It actually comes from an isomorphism of the underlying projective varieties over the power series ring. So in other words, if I'm given sort of the analogous statements, when I'm given two finitely generated modules over a polynomial ring, or over, let's say, a localization of a polynomial ring, then if I have an isomorphism of a compatible system of isomorphisms between m and n mod t to the n, if m and n are finitely generated, it comes from an isomorphism of m tensor power series in t to n tensor power series in t. And this is just sort of the projective variety version of the statement. And this is false if you don't have a projective variety. If you take the affine line or something, because the affine line, this coordinate ring, is a polynomial ring which is an infinitely generated module. And so it's just absolutely false. Okay, so now you have this isomorphism over the power series ring, but now there's a theorem of Artin approximation, which was precisely designed when people were thinking about deformation theory and the like for this problem, which is to say, in this situation, let's call this isomorphism phi or something. Phi is induced by an isomorphism over some étale extension of the local ring OCP. And this actually really, in this case, you don't need really the full strength of Artin approximation. In some sense, it comes down to the fact that the sort of isomorphism of the projective varieties are given by schemes which are locally of finite type. But anyway. Okay, so, and I mean, some metal extension, we call it A, and then the fraction field of A, say K prime of A, then has the property that if I look at X tensor, in other words, if I now, I have A, I pull back my family here, spec A, this is étale, I pull back the family over this and it becomes trivial. Okay, so you might say, what on earth does this have to do with the field of moduli? So I'll try to explain that in the last 22 minutes. So a little ring, little k, or it's just a little k algebra, just in the weak sense. And so that dt is a derivation, a higher derivation over k if di of f of r equals 0 for all I greater than 0. Okay. So you can certainly talk of delta r over k. This is the group of higher derivations of r over k. Now, what does this have to do with the automorphisms? So we can look at the field, or in fact, well, any ring, but let's actually look at the let's look at this situation. If R is a ring, is a K algebra. So how should one think of this group? Well, you can look at the following thing. Let me just make the sort of remark that if X is a scheme over K, or it's a variety over K, and A is a K algebra, then you have X of A is just the homomorphisms from spec A over K, little k, to X. So in fact, if X equals spec, let's say, of B, then this is just hom of algebras from B to A. So for example, AN takes A to just A1, AN in just A to the N. So the point here is, if we're given a scheme or a variety, we can over K, we can really think of this. So variety or schemes over K embed into functors from K algebras to sets, and this is contravariant. Or another way to say a scheme is your contravariant functor. Let's be careful, I said this is a contravariant, wrong place. Yeah, I think I'm saying that right. so now there are conditions on a functor to be a scheme, which I'm not going to worry about right now.
I think it's not covariant, maybe because his spec becomes contravariant, but then
Okay, well let's test this. So if I'm given a functor, if I'm given a homomorphism b to b prime, and I'm given, I mean, better precisely reflects the fact. So, well, there are two different things. Okay, so certainly for a scheme, you get a contravariant functor from K algebras to sets. If I'm given a homomorphism, I'm given a value point to B, or sorry, B prime. That's a homomorphism from B prime to A. And induces a homomorphism from B. So maps from hom B prime to A to hom B A. In any case, so there's an interesting point, which is that there are certain people, since there are probably no differential algebraists here, I won't get into trouble for saying this, but there are people in the differential algebra community who have spent a lot of effort trying to come up with what's the right notion of a differential scheme. What they don't seem to realize is that by sometime in the mid-60s, Grothendieck wasn't interested in schemes anymore. Anybody who's read the second edition of EGA, the Springer version of EGA, and looks at the introduction, it's this point of view that Grothendieck really wants to emphasize. And so why do I say this? Well, we can just sort of think of a functor like this as some kind of generalized scheme. And then we can worry afterwards whether it has nice properties. Okay, what's an example of this? So we've got our K algebra R, and we can look at the automorphisms of definition. Ought, now I'm going to write this in script letters, is the functor which sends A the automorphisms over A of A tensor over K to the R. Now, in very special situations, this is actually a scheme. If, let's say, R is a finitely generated K module. So, e.g., so here are some examples. So I look at the automorphisms over kt to the p or k of t, which is isomorphic to alpha p. So the additive subgroup, the group of sort of p torsion elements in the formal additive group, the automorphisms over k of L, if L over k is Galois, is just the Galois group. L over k is just a discrete group. So it's a discrete group scheme. In general, if you take something like the affine line, this is a kind of pretty nasty object. So this obviously extends to schemes over what I would say, this extends to schemes over K. Right. So if X over K as a scheme, you still look at sort of the automorphisms over K of X. And if X is projected, this is basically a disjoint union of schemes of finite type. So, for example, if X is an abelian variety, in general, this is a discrete group, but it's generally, it's generally speaking, an infinite discrete group, or can be an infinite discrete group, if the abelian variety is complex multiplication. If X is projector space, this is just, P, PGL2K. So in general, this is some sort of, for a projective variety, this is a disjoint union of algebraic groups. And for other schemes, it could be something completely horrendous. Okay, so sort of the moral in the last 2 minutes, and I'll continue with this next time. So the moral here is that in the original definition of the field of moduli, you just looked at automorphisms in the classical sense. And really, one has to look, in some senses, at the full functor of automorphisms. And again, the moral was that you don't have a good notion of sort of minimal fields of definition if you look at the field of moduli, if you look at discrete phenomena. And I think in some sense the the statement is if you look sort of at the connected component of the group of automorphisms, then you have a good theory. And why is that? So this is sort of the final thing I'll say today, to link this up with higher derivations, is that if X is a scheme over K, and D from OX to OX is a higher derivation over K, so i.e. the DI or K linear sheaf homomorphisms such that if F and G are an OX of U, the DI of FG is the sum DJ F DKG J plus K equals I. So that encodes the fact that D sub T is a ring homomorphism, and such as 1, 2, D0 is the identity. Then this, sort of by the remark that I made on the board over here, that if you're given a higher derivation, it gives you an automorphism of the power series ring. This data, so D determines I should put in parentheses, formal KT value point of the automorphisms over K of X. So in other words, i.e. compatible system so in other words, if I have such a point, well, so in other words, if you think of this, you have this function, you have this sort of thing you should, in some sense, think of as a scheme, a group scheme. So sort of here it is, here's this group scheme, and then this thing is giving you, here's the identity, and this thing is giving you some sort of arc, formal arc in the group scheme. And of course, if I'm given a formal arc, and these KT mod T to the n value of points have the property that when you set n equal to 1, you just look at the sort of mod T completely, it's just the identity. So at T equals 0, it goes to the identity. You get two such arcs. You can just multiply them with respect to the group law. And this is this, they go to, oh no, here it is. So this sort of delta, if you like, is the group of formal arcs and the identity in alt k x. So actually, maybe if I can take 1 minute, I should, since I sort of this whole thing at first, our has been basically definitions, I should at least state a theorem. So the theorem is that x is a projective variety over k, with k the separable closure of a field finitely generated over the prime field, and k descends to k delta, maybe I should sort of k, maybe kg, where g inside delta k over, I should give the prime field a name, little k0, is the subgroup of derivations which lift to OX. So next time I'll talk about the truth of this result. That's it.
Questions? Yes. Oh, I was typing. That's, I think, quite bored.
Given that I had a beer at lunch, it might be better you didn't.
Because of questions.
I have a short question. Can you mean that the cabo group, G acts like derivation here? It is subset of this derivation, yeah?
Sorry, well, I mean, D1 is a derivation. So in other words, maybe I should, this is a good point. I mean, what are the derivations in the classical sense, right? The derivations in the classical sense are tangent vectors at the origin here. And so the Lie algebra of derivations is the Lie algebra of this group. Leaving aside the fact the group is a functor and not a scheme, but who cares? No, I mean, seriously, if you take a group value functor, if you have a group value functor from K algebras to groups, and just evaluate it on K epsilon, where epsilon squared equals 0, what you get is precisely a Lie algebra. So I mean, I think that hopefully that kind of connects with what you were asking.
So, another question? Okay, yes, thank you.